All right, so the game plan is to do 7.8 today. I was done with 7.7. I did 3 out of the 6. I think that's enough. So 7.7, right? You had the midpoint rule, the trapezoidal rule, and Simpson's rule. Let's make the standard that you go 6 digits to the right of the decimal point. Well, unless it comes out nice, like they were all 0, you don't have to put 0.000000, just put 0. But if there are digits, then go up to 6. That would be good enough. Okay, so I would pretty much be done with the chapter today, hopefully. If not, maybe just a minor part for next time. The main thing is I wanted to make sure that you had enough of 7.8 so you know what's going on before the test next Thursday. And that kind of goes along with this. If I waited until Tuesday to do any of 7.8, you'd only have 2 days to prepare, but now this way you have a week to prepare. Okay, so I'll do as much of 7.8 as possible, maybe all of it, and then at the very end of class we'll have our quiz, and that's it. So what's on the schedule for next Tuesday? I'll either finish 7.8 or I will just get started with an 8.1 and go from there. I'm not moving up the exam. The exam is still going to be next Thursday. All right, so now that you've already had one exam, you know what it's about. So you turn all of this in for homework. There's the 70% homework requirement. You have to turn in at least 70% of the homework. Hey, I end up doing what, 30, 40% of the homework, 50% of the homework in class anyway. So it should not be that hard for you to fulfill the 70% requirement, right? Okay. So again, the schedule, next Thursday, I'll start off with lecture. I'll keep going with 8.1 or 8.2 or whatever case may be. After a certain amount of time, I'll stop and questions and answers. And let's make the limit for that should be what, 8:20? 8:20, so we'll break for 10 minutes, 8:30. That'll still give you 50 minutes, 55 minutes to do the exam. If we end the first half early and break early, then that's fine with me. Then you'll just have more time for the exam. Okay. Then after the break, we'll break as normal. During the break, I will probably send through Canvas announcements or email. I'll give you the exam there. I'll also project it like this to give you 2 chances. So maybe you can't access your Canvas announcements for whatever reason. I'll project it like so. So you can take a picture or do a screenshot. But if you want to get it off Canvas announcements, you can open that file and print it out. Maybe it's easier for you if you print it out. And then you work on it. And your homework is due next Thursday also. If you want to submit it earlier that day, that's perfectly fine. I'll let you do that. And then class is over at 9:25, right? So you have until 9:30. Click, 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 take a picture of all your pages, or if you have a scanner or a CAM scanner, you can submit that. So 9:30 for the exam, and then another half an hour, so 10 o'clock p.m. you have to submit the homework. But if you want to submit the homework early, that's fine. And what else? You know the rules. So exams, you will mute yourselves, but have your camera on. You must have your camera on. I need to see what you're doing, obviously, okay, for that. Let's see, how many questions? I tend to give about 10. So again, 10, that's not a promise, maybe 9, maybe 11, but about 10. We're gonna have the same amount of time. So you will have 15 minutes. That's all I'm promising. That's really up to you guys. So the latest I'll stop the first half is what, 8:20, we said? That way we can start at 8:30, then 5 minutes to get started. So 8:35 to 9:25. But if you all want to break earlier and then start earlier, you can do that. So that's up to you. Okay. All right. So I think I'm caught up with the chat there. All right. So we're here, 7.8. So again, I've managed to get a little bit ahead, but we already have seen that. I said last time, it's good to be ahead in case something goes wrong. Well, something's already gone wrong. I was down for a week, right? So just in case, or I might get sick or whatever. So just because I'm ahead, we're not going to stop. We're not going to take a vacation. We'll just keep going in case something, quote unquote, goes wrong again, right? All right, so I'll go ahead and get started with 7.8. And so let's see, there were 6 sections. So obviously you're going to get 1 question from each. And if I give you 10 questions, then, you know, some other sections will get 2. And there we are. All right. Okay, let's see. Breaking early before, that's up to you guys. The test time wasn't enough. Well, that's subjective, but I promised you in my syllabus 50 minutes, so I gave you 50 minutes and more. Okay, so that's up to you. All right, so you have to finish by, the only thing I'm promising you is 50 minutes. So that's why the latest we're going to start the test would be what, 8:30? Because it takes 5 minutes to get started, and then 8:35 to 9:25. Okay. All right, so I think we're ready to start some math now. So 7.8, it's on something called improper integrals. So 7.8, the topic is improper integrals. Improper integrals, page 527 is where it starts. And by the way, that seems to imply all the integrals we've been doing so far are proper, which is correct. Okay, so we've only been doing proper integrals. So what is this improper integral stuff? Okay, and for those of you that need it, here's the homework, page 534, for those of you who never plan to get the book. Okay, so there's some of the problems. Well, actually, yeah. There's all the problems from that page. Okay, and then the next page, 535 it looks like. Some more there. And I don't think we have anything more after that, so that's that. Okay. All right, so improper. So why improper? Okay, I'm not sure if you can see some of these, but if you can see it, or if you have the book, you can see it. One thing I notice is that there's infinity, or sometimes there's negative infinity, or sometimes they have both. All right. So one thing that makes an integral improper is to have infinity involved. Okay. That's not the only situation, but that's a situation. Okay. All right. So improper integrals. Whoops, my chat box is too big. Make it a little bit smaller. Okay, integral from 0 to infinity of f of x dx. Okay. Now, how do you do that? Well, the concept is this. We know that for definite integrals, like if we're going from a to b, then we just have area under the curve from a to b. How about if we go from 0 to infinity? So let's say there's a function like this. You start at 0, and you never stop. You keep going as far as you can. That's what it means to go to infinity. Okay? Now, you might think, well, if I'm going infinitely far, am I going to have an infinite amount of area? Well, it depends. It's not guaranteed. So here's the way we're going to define it. So integral from 0 to infinity. We will stop after some value b. I'll put capital B standing for a big number. Maybe it's 1,000,000, maybe it's 1,000,000,000, 1,000,000,000,000, or whatever. Okay. I will take the integral from 0 to b. Okay, so if I take the integral from 0 to b, now it's defined. Your expression will have something involving b. And then I take the limit as b approaches infinity, you see. And we know how to do that from Calc 1. Okay, so if I integrate from 0 to infinity, I'll take the integral from 0 to b. You're going to plug into b, and then take the limit as b approaches infinity. That might be infinity. It might be a real number. Okay, whatever. So anything is possible. All right, so let's get started with an example. So we will define this integral as such. If we have integral from 0 to infinity, we'll go from 0 to b, and then pull b to infinity. So limit as b approaches infinity as the integral from 0 to b of f of x dx. Okay. And in case you want to see it in the text, although I'm not sure you can see it. Okay, so the integral from a to infinity is the limit from, as t approaches infinity, they use t, other versions use b. I'm using b for a big number. Integral from a to t of f of x dx. Okay. Likewise, if you have a negative infinity involved, integral from negative infinity to some b, you go from t to b, and then take the limit as t approaches negative infinity. Okay. If you can't see it, don't really worry about it. It'll become obvious once I do some problems of how to tackle it. Okay, so let me do some problems right now. Okay, so question 3. Integral from 3 to infinity of 1 over x minus 2 to the 3 halves dx. Okay, I put a quick graph here. And by the way, you say, well, how do you know the graph looks like that? Well, you just need some key things. They started at 3. So what do you get when you plug in 3? 3 minus 2 is 1. 1 to the 3 halves is 1. 1 over 1 is 1. So 3 comma 1. And I know if I plug in bigger and bigger and bigger numbers, plug in a million, a billion, a trillion, this expression approaches 0. Okay, so it drops like that. Okay, so on the one hand, you might say, well, there should be an infinite amount of area because I'm going infinitely far out to the right. Yeah, but on the other hand, the amount that you're adding is smaller and smaller and smaller and smaller. So do I get all the area that I want or don't I? All right, so here's what we do. For the integral from 3 to infinity, I change it from 3 to b. So here's b. B represents some big number. And then I take the limit as b approaches infinity. All right? So how do I integrate this? Change it to x minus 2 to the negative 3 halves. Okay? And by the way, you don't have to do a substitution because the derivative of x minus 2 is 1. You don't have to worry about the chain rule. Okay? Just go ahead and do your power rule. All right. So power rule, limit as b approaches infinity. X minus 2 to the negative 1/2 divided by negative 1/2. If you divide by negative 1/2, it's the same as multiplying by negative 2. So I put the negative 2 here, which I'm allowed to take outside. Okay, one of the properties on Calc 1 is if you have a limit of a constant times a function, you can take that constant outside. All right, so again, x minus 2 to the negative 1/2 divided by negative 1/2, right? You add 1 to the exponent, divided by negative 1/2, multiplied by negative 2. Bring the negative 2 in front. And what's the meaning of x minus 2 to the negative 1/2? It means a square root in a denominator, so 1 over radical x minus 2. All right, so negative 2, limit as b approaches infinity. Plug in b, 1 over radical b minus 2, minus, plug in 3. 3 minus 2 is 1. Square root of 1 is 1. 1 over 1 is 1. So I have that. All right, and now what happens when b gets real big? Plug in a million, a billion, a trillion. This expression approaches 0. That's what I mean by putting that 0. So I have negative 2 times negative 1, which is equal to 2. All right, so I do have a real number 2. Okay, so if I go infinitely far out, you'll never get past 2. So if I stop anywhere, if I stop at x equals a billion, we're really, really close to 2. Maybe it's 1.99999, and you'll never get past 2. The language we will say is that the integral is 2. Okay, and more language. If you get a real number in your answer, we will say that the integral converges or is convergent. The integral is convergent if we get a real number. Okay? If we don't get a real number, or like it comes out to be infinity, then we will say that the integral diverges or is divergent. Okay? We'll use that language of converges and diverges much more in our last chapter, chapter 11. Okay, but for now, right, so fancy language. If you get a real number for this limit, okay, we know sometimes the limit comes out to be infinity or the limit doesn't exist. Okay, so if this limit comes out to be a real number, we will say the integral converges. In this case, we say the integral converges to 2. If we do not get a real number, the language we will say is that the integral diverges or is divergent. Now that includes going to infinity, but it doesn't have to go to infinity or negative infinity. It can just not approach any real number. Okay. Okay, so let's do some more of those. 11. Integral from 0 to infinity of x squared over radical 1 plus x cubed dx. I'm not going to bother with a picture for this one. You know, it's not necessary. But we do the same thing. Instead of going from 0 to infinity, I'm going to go from 0 to b and then take the limit as b approaches infinity. And I notice, what's the derivative of 1 plus x cubed? 3x squared. I have the x squared. I don't have the 3, but I can always put a constant inside and outside. So this is a regular U substitution. Okay, so let U equal 1 plus x cubed. Du equals 3x squared dx. Okay, I see the x squared. I see the dx. I don't have the 3, but we know the way the game works. 3 here, 1/3 here. By putting both of these, I've multiplied the expression by 1, which means I get an equivalent expression. And I take the 1/3 out. Again, you can take constants in and out of a limit. Okay, and I'll change these limits also. 0 to b is for x, but now I want to know what happens to u. So when x is 0, the lower limit, plug in 0 right here. 1 plus 0 cubed is 1. So u is 1, the bottom limit. When x is b, you can just leave it as b. When x is b, u is 1 plus b cubed. Yeah, just leave it as 1 plus b cubed, that whole thing. It's the best we can do. So now my integral has a 1/3 in front of it. Limit b approaches infinity. Integral. Okay, 3x squared dx. 3x squared dx. So pretend you erase this whole thing, put du. Radical 1 plus x cubed. 1 plus x cubed is the same as u. So instead of radical 1 plus x cubed, get your eraser, so to speak, and erase that. And now I have radical u. And that's a fairly easy integral. Okay, equals 1/3. Notice you keep writing limit. You should keep writing limit all the time. I'll take off if you don't have that. That's proper way to write mathematics, so to speak. Limit b approaches infinity, integral from 1 to 1 plus b cubed. So in order for me to make the power rule, write that as u to the -1/2 du. All right, so that should be pretty straightforward. Integral of u to the 1/2. Power rule, you add 1. U to the 1/2 divided by 1/2. There it is. Divided by 1/2 means multiply by 2, right? Okay, so again, power rule, you add 1 to the exponent and divide by the new exponent. So -1/2 plus 1 is +1/2. Divided by 1/2 means times 2. And again, I'll bring the 2 outside with the 1/3. So now I'm going to have a 2/3 in front. And then u to the 1/2 means radical u. Square root of u. And from 1 to 1 plus b cubed. All right, so 2/3 is in front. Limit b approaches infinity. Okay, radical. Plug in 1 plus b cubed. So 1 plus b cubed goes right there. Minus, plug in 1, square root of 1 is 1. And now what happens for super big b? Your real big number, square root is still a big number. Subtract 1, it's a big number. Multiply it by 2/3, it's still a big number. This limit is infinity. Or we would say the integral diverges in this particular case. Okay, so the integral diverges. So here's an instance where you get an infinite amount of area. You can have all the areas that you want. So you want 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000 square units, you've got it. Okay. Not true for this one. This one you can't get past 2. Okay. So if you stop at 1,000,000, 1,000,000,000, 1,000,000,000,000, you're probably at 1.99999, but you can prove mathematically you can never get past 2. So the language we would say is that this integral is equal to 2, or that the integral converges to 2. In this case, not so. Whatever this thing happens to look like, it's very messy. But whatever it looks like, you get an infinite amount of area. You can have all the area that you want in this particular case. Okay. All right, so that's that one. So I've given you 2 cases where we have infinity. Okay, now let me give you a case with a negative infinity. So 7, integral from negative infinity to 0 of 1 over 3 minus 4x dx. Okay, so this time we have a 0 here, but we don't have any fixed number on the left. So carry this thing way out to the left, infinitely far to the left. Which means this time I'll have a b way out to the left. So b is like -1,000, -1,000,000, -1,000,000,000, -1,000,000,000,000, right? And now we're letting b approach negative infinity. I have a quickie graph here. You don't really have to graph it, but How do I get it? Again, so they have 0. So what do you get when you plug in 0? 1/3. And if I plug in a super big negative, like negative a billion, let's see, if I plug in negative billion, 3 minus 4 times negative a billion, you got a double negative, so I have a super big positive. So 1 divided by big positive is small positive. Okay, so it does look indeed like that. All right, so again, I have the conflict. I'm going infinitely far to the left. So on the one hand, you might say, well, don't I have an infinite amount of area because I'm going infinitely far? Well, not necessarily, because the amount that you're adding each time is smaller and smaller and smaller, right? So we don't know offhand. All right, so this time b is the lower limit. So I take the integral from b to 0, and then the limit as b approaches negative infinity. Okay, so when you have a negative infinity, put b in the bottom, because b is going to be on the left of 0. Limit as b approaches negative infinity, the integral from b to 0 of 1 over 3 minus 4x dx. Okay, now this is going to be our natural log situation. So limit b approaches negative infinity. Okay, ln absolute value of 3 minus 4x. And now the chain rule, if I were to differentiate at this stage, I would multiply by negative 4. Since I'm integrating, I divide by negative 4, or you can say multiply by negative 1/4 as you go from b to 0. Okay, so one more time, remember the chain rule for derivatives? If you had an expression like this, 3 minus 4x, at that stage, if you're trying to find its derivative, you would multiply by a negative 4 by the chain rule. Since I'm integrating, you do the opposite. Instead of multiplying by negative 4, divide by negative 4, which is the same as multiplying by negative 1/4. Okay? And still another way you can think about it that should answer all questions is, well, what's the derivative of this expression? Okay, so ignore all that. What's the derivative of this? Right? You would go negative 1/4. 1 over is the derivative of ln something, right? So 1 over 3 minus 4x, and then by the chain rule times negative 4. Well, if you multiply by negative 4, that cancels out that negative 1/4, and so you do have indeed 1 over 3 minus 4x. So yes, indeed, the derivative of this thing here is 1 over 3 minus 4x, so it definitely works. All right, take the negative 1/4 out in front again, so I pulled it out. All right, so limit b approaches negative infinity, that's a b there. Okay, plug in 0. Well, let's see, I have 3 minus 0, which is 3. Absolute value of 3 is 3, so ln 3 minus ln, well, absolute value of 3 minus 4b. Okay, now you plug in a super big negative number. Okay, see if you can follow this progression here. Let's see. This is a super big negative. 3 minus 4 times a big negative is a big positive. Okay. If it helps you, think of plugging in negative a trillion. 3 minus 4 times negative a trillion, double negative, super big. ln of big is big. Okay, so just right here, big positive. How about ln 3, which is a very puny number? You can punch it out on your calculator, but it doesn't really matter. It's a small number compared to this. ln 3 minus a super big number. Now this whole thing, everything in here, everything between my two pens, is now a big negative. Okay, so one more time. I claim 3 minus 4b is a big number. ln of big is big. ln 3 minus big is now a big negative. So negative big times negative 1/4. Negative 1/4 times negative big number, that's infinity. All right. So once again, we have an infinite amount of area in this situation. You get all the area that you want. Okay. And yes, the language would be, we could say that this integral diverges. Okay, I'm not putting that down now, but we say the integral diverges. Okay, next thing I want to show you is what happens. See, I don't want you to think that divergence always means infinity. You could have divergence that doesn't go to infinity. You just don't approach any real number. Okay, the next one's a good example of that. Integral from 0 to infinity of sine squared alpha. Okay, in case you haven't seen it, this is the Greek letter alpha. It's the first letter of the Greek alphabet. Okay, so that funny thing is alpha. Sine squared alpha d alpha. All right, so we go from 0 to b, take the limit as b approaches infinity. All right, so a while back we did this. You're going to need this for next Thursday's exam, right? This falls into the category of sines and cosines that only have even exponents. So I have to use that identity for sine squared, 1 minus cosine 2 alpha over 2. Limit b approaches infinity. Okay. All right, take out the half. Half comes out. Limit b approaches infinity. All right, integral of 1 d alpha is alpha. Sounds funny to just say d alpha, but that's the way we have to do it. Okay, what's the integral of negative cosine? Negative sine 2 alpha. And then the chain rule again, I see 2 alpha. So if I were differentiating, I would multiply by 2. Since I'm integrating, I multiply by 1/2. So alpha minus 1/2 sine of 2 alpha. Okay, so I plug in b. b minus 1/2 sine 2b minus 0 minus sine of 0 is 0. Okay, and how do we analyze this one now? Well, what do I know about 1/2 sine of 2b? Sine of anything. Sine of any angle is always between -1 and 1. Now I multiply by -1/2. So this expression is between -1/2 and +1/2. But that gets big. Okay? So a super big number, you're either going to add or subtract 1/2. That's like nothing. Multiply the whole thing by 1/2. That's infinity. So once again, I get a case of infinity. Okay. All right, the next one is a case where you have both negative infinity and positive infinity. Number 13. Okay, so it's from negative infinity to positive infinity, x e to the negative x squared dx. Okay, so how do I do that? First, I did myself a quick graph. Okay, what do you get when you plug in 0? 0. Okay. Recall e to anything is always positive. Okay, so that's always positive. So if x is positive, the graph is positive, first quadrant. If x is negative, we already said this is positive, it'll be negative, so quadrant 3. Okay, furthermore, if I replace x by negative x, put negative x right there, negative x right there. Well, the opposite of negative x squared is still negative x squared. That's the same, but that would have a negative in front of it. Okay. In other words, f of negative x is the opposite of f of x. That tells me I have an odd function. Okay, so this is odd because f of negative x is the opposite of f of x, which means I have origin symmetry. I have symmetry with respect to the origin. All right, well, how do you go from negative infinity to infinity? Well, I can break it down into negative infinity to 0, and we already know how to tackle that. That's like this one. Plus the integral from 0 to infinity, and we already know how to tackle that. All right, we've done some of both of those. Okay, so whenever they give you an integral from negative infinity to infinity, you can go from negative infinity to 0, plus the integral from 0 to infinity. Now, very technically, you could put any real number here. You could say go from negative infinity to pi, and then pi to infinity, or negative infinity to 45, and then 45 to infinity. But usually it's easiest to go to 0. Okay, now, at first glance, okay, ignore that 1/2 and -1/2 there for now. Okay, at first glance, you might say, oh yeah, by symmetry, that's going to match that. And since this is below the x-axis, this is above the x-axis, the answer should automatically be 0, right? Not necessarily. Okay, because this is how we're defining the integral from -infinity to infinity. Okay, we break it into these. This might be divergent. This might not exist. If it does exist, then yes, I can say by symmetry, this would just be the opposite. So the answer is 0. Okay, so at this stage of the game, even right now, there's only 2 possible answers. Answer number 1, the integral diverges. Okay, if this doesn't come out to be a real number, which therefore means this won't come out to be a real number either. The other possible answer is this does come out to be a real number, and then we can say by symmetry, this would just be its opposite, so the answer is 0. Okay? But just because I have the symmetry, don't automatically assume that we have the answer to be 0. We have to make sure that this exists and this exists. So you can get by with either one of these. Okay? Can you guess which one I'm going to do? I like this one because it's got positive, right? So integral from 0 to infinity. All right, so I'm going to call this I2. Okay, I'm going to break this up into I1 and I2. This is I1. This is I2. Yeah, I've already given you the answer. It's a half, but pretend you don't know it yet. So I'm going to do I1 plus I2 is equal to the entire integral. I'm only going to work on I2. Okay, so I2, integral from 0 to infinity. X e to the negative x squared dx. Okay, which is the limit as b approaches infinity of the integral from 0 to b of x e to the negative x squared dx. Okay, what is the derivative of negative x squared? Negative 2x. There's the x. I don't have the negative 2, easy. Negative 2 inside, negative half outside, right? Okay, so you can always put a constant inside and outside. Now you can't do that for variable expressions. So let's say you only have e to the negative x squared. Okay, we had something kind of like that in the approximate integration that we did the other day. I think it was e to the positive x squared. Remember, we had to do the midpoint, trapezoidal, and Simpson's rule, right? Okay, there's no way to integrate this normally, quote unquote. We'll learn a technique in chapter 11, our last chapter, but right now there's no way to do this. But here with an x, you can do a u substitution. Let u be negative x squared. The derivative is negative 2x dx. Okay, there's the x, there's the dx. I need to put negative 2 and negative a half. Okay, and I have to check my new limits. Okay, so 0 and b are for x. So now what's going to happen for u? So I plug in. When x is 0, put a 0 right there. Negative 0 squared is still 0. Plug in x is b, u becomes negative b squared. So here we go. Negative a half, I2, put it in front, negative a half. Limit b approaches infinity. I'm no longer going from 0 to b. I'm now going from 0 to negative b squared. Okay, so e to the negative x squared is now e to the u. And negative 2x dx, negative 2x dx, pretend I erase that, negative 2x dx, negative 2x dx, I will substitute for du. And now that's very easy. Okay, so what's the integral of e to the u? E to the u. So negative 1/2, limit b approaches infinity, e to the u from 0 to negative b squared. Okay, so I get negative 1/2, limit as b approaches infinity of e to the negative b squared minus e to the 0. E to the 0 is 1. Okay, if I plug in a super big number, a million, e to the negative million squared, that's practically 0. Okay, I crossed that out. Maybe I should cross that up and put a 0 here. Okay, e to the negative million squared, practically nothing. Remember, that's the same as 1 over a big number. So I have negative a half times negative 1, which is equal to 1/2. Okay, so now getting back to here, I put the half here. So now I know this area, if I go infinitely far, remember you're going all the way out to the right, that's 1/2. And therefore, by symmetry, I'm not going to actually integrate this. I can say by symmetry, and this is below the x-axis, that's going to be negative a half. So I can say the final answer is 0. Okay, so here is now what I have. Negative 1/2 times negative 1 is 1/2. So I2 is 1/2. By symmetry, I1 is equal to negative a half. So therefore, I is equal to I1 plus I2, which is negative a half plus a half, or it's equal to 0. Okay, so back over here, we now know this is a half, this is negative half, so we can say the integral is 0. But let's say this came out to be an infinite number, a super big number, then we wouldn't be able to say this. There's no such thing as infinity minus infinity. So we would say that this integral diverges. Okay? We don't get a real number answer because this is not a real number. And likewise, by the same token, this is not a real number. Okay. All right, so there we go with that one. Okay, I'm now going to show you something called 27 star. Okay, that's not in the book. That's not 27. That was in the 7th edition, but it does illustrate something. Okay, so there's other types of improper integrals. Okay, so improper integrals, I can have infinity. I can have negative infinity. I can have both. But that's not the only type of improper integral. So I'm going to show you 27 star, which means it was problem 27 in the 7th edition. Okay, take a look at this. Integral from 0 to 1 of 3 over x to the 5th dx. Okay. Now, there's no infinity, there's no negative infinity. So what's quote unquote wrong, or what's improper about this one? Well, I see 0 here. I cannot plug in 0, right? Let's take a look at the graph. You plug in 1, 3. I'm not allowed to plug in 0, but I can plug in 0.000001. 3 divided by a super small number is real big. So here's a quick graph of this function. Okay, so 1, 3, and it shoots up, 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 all the way up. And so I'm considering the area right in here. So this time the question is, right, as I'm going super far up, do I get an infinite amount of area, or I don't get an infinite amount of area because I'm kind of getting squeezed in again, right? It's a conflict. You might say, well, I'm going infinitely far up. I should get an infinite amount of area. Not necessarily, because the amount that you're getting is less and less. Okay, so here's the strategy this time. Okay, so I can't make heads or tails about 0, but if I move a very small amount to the right, I'll call it B. Even if B is 0.000001, this thing is defined, right? There's going to be a point. It's going to be way up here maybe, but it is defined. So I will integrate from B to 1, where B is a number real close to 0, and then take the limit as B approaches 0 coming from the right side. Remember in Calc 1, right? You have one-sided limits. We had two-sided limits, right? And we also have one-sided limits. Remember in Calc 1, you can come either from the right side or you can come from the left side. Two-sided limit means you're coming from both sides, right? So if I just say limit B approaches 0, remember that from Calc 1? Limit B approaches 0, that means I'm coming from both the left and the right. Okay, but here, I'm only interested in coming from the right side. So I'm pushing B closer and closer and closer to 0, coming only from the right in this particular case. Okay, so integral from B to 1. So how do I interpret the integral from 0 to 1? Because 0 is not defined. I'll take the integral from B to 1, and now B is defined. Right? There will be a point on the graph here. I'll figure this out, and then let B approach 0 coming from the right. Okay. All right, so again, change that to 3x to the minus 5. So what does that give me? 3x to the minus 4 over negative 4. Limit as b approaches 0 coming from the right, from b to 1. Okay, take out the constant. So negative 3/4, bring it out in front. Limit b approaches 0 from the right. X to the minus 4 means 1 over x to the 4th, from b to 1. Okay, so negative 3/4, limit b approaches 0 from the right. Okay, but when you plug in 1, I get 1 over 1, which is 1, minus b to the 4th. Okay. All right, so here's this situation again where you have to follow the logic. B approaches 0 from the right. 0.00000001. Okay, so follow the logic here. Plug in 0.001. 1 over that is a big positive. Okay? If B approaches 0 from the right. 0.0001, big positive. Big negative. 1 minus that, big negative. Okay? So I have 1 minus a super big negative, 1 minus a super big positive is now a super big negative. So this expression between my two pens is a big negative. Big negative times negative 3/4, big positive. So positive infinity. All right, so in this particular case, you do get an infinite amount of area. You get all the area that you wish up here. Okay. All right, so I wanted to show you that as a first example. So improper integral could mean negative infinity, positive infinity, or both. But the other types of improper integrals, you could have a real number here and a real number here. But what makes this improper is you can't plug in 0. But you can still do the integral, because we're going to say go from b to 1 and then let b approach 0 coming from the right. Okay, so now we have some other problems in the text that are kind of like that. Oops. So 27 is like that. Integral from 0 to 1 of 1 over x dx. 29 and 31 are kind of like that also. Okay, so I'll show you a couple of those. Okay, 27, and this one is in the book. That's in the 8th edition also. So we'll check if that's the case. Yeah. Okay. All right, integral from 0 to 1 of 1 over x dx. Here's the picture. We know what 1 over x looks like. So this is a 0. Okay, you can't plug in 0, but as I go higher and higher, do I get an infinite amount of area or I don't get an infinite amount of area? Well, we don't know. Okay, so I just put a b. B is really close to 0. If I plug a number like 0.000001, this is defined. So I take the limit as b approaches 0 from the right. So b is sort of like this. It's real close to 0. Now it's defined. I figure this out. Limit as b approaches 0 from the right. Integral from b to 1 of 1 over x dx. Okay. All right, that's my natural log. That's about as straightforward as you can get. So limit as b approaches 0 from the right, ln absolute value of x from b to 1. Plug in 1. Absolute value of 1 is 1. So I have ln 1 minus ln absolute value of b. Limit as b approaches 0 from the right. Now, ln of 1 is 0. Do you recall what's the graph of ln x? Okay, I'll put it right over here, very crudely. The natural log function looks like this. Okay, so what happens as b approaches 0 coming from the right. If I come from the right side, the y values drop to negative infinity. Okay, so absolute value of b, well, I'm only plugging in positive numbers, so the absolute value of b is the same as b. Okay, so this right here is a big negative. Okay, one more time, b approaches 0 from the right. If you look at the graph, when b approaches 0, y drops to a negative infinity. So right now, this is a big negative. Now I have a negative in front of that, and this is 0. So I have negative, negative big, so positive big. All right, so answer is infinity. I do get an infinite amount of area in this situation. Okay. Let me see. Okay, so I have here called 31 star. Or do I want that? Well, it's kind of close. Instead of -2 to 1, it was -2 to 3. Yeah, -2 to 3. I've got -2 to 1. Well, I'll do it. It's almost the same thing. All right, so 31 star, what time is it? Okay, so maybe we'll break after this one. -2 to 1, they have 3, but it's the same idea. Now, what's wrong with this one? 1 over x to the 4th. I can plug in -2, no problem. I can plug in 1, no problem. So what's the issue? The issue is that you have to pass through an undefined point, right? What number is not allowed here? 0. So there's no problem with -2. There's no problem with 1, but there is a problem with the number that I have to pass through, namely 0. Okay, so let's say this was -2 to -1, -2 to -1, that's an ordinary integral. Or if I were going from +1 to +2, it's an ordinary integral. What makes this improper is you have to pass through 0. Okay, so we'll split it up as follows. I'll take the integral from -2 to 0, and I know how to do that. And then I take the integral from 0 to 1, and I know how to do that. Okay. Now in this case, if I were going to take the integral from -2 to 0, I'd put b here, and then I would let b approach 0 coming from the left side, approaching from the left. This one is the same as usual. Now, if either of these comes out to be infinite, I don't have to do the other one. I've got an I1 and an I2. We know that. If there's an infinite amount of area here, it doesn't matter if this one is infinite or finite. Okay, let's pretend this is infinite. This came out to be 5. Well, a big number plus 5 is still infinite, right? But let's say this one comes out to be 5, and this one comes out to be 10, then I just add them together. Okay, but one of them is infinite, I can stop. If this is infinite, big number plus big number is big number. But if one of them is infinite and the other is a real number, it's still big, right? Okay, so I was going to work on I2 first. Okay, so working on I2 first, integral from 0 to 1. Yeah, the book has 0 to 3, but I think it comes out to be almost exactly the same. So I2, that's like the previous one. So b has got to be on this side. So I take the limit as b approaches 0 from the right. So you're coming this way. Integral from b to 1. 1 over x to the 4th is x to the -4 dx. All right, so limit as b approaches 0 from the right of x to the -3 over -3 from b to 1. Take out the -1/3. Right, -1/3. Limit b approaches 0 from the right. X to the -3 is the same as 1 over x cubed from b to 1. Okay, -1/3. Plug in 1, you get 1. Plug in b, you have 1 over b cubed. So -1/3, limit b approaches 0 from the right of 1 minus 1 over b cubed. Okay, so same game as before. Okay, b approaches 0 from the right. So 1 over b cubed, plug in 0.0000001. This is a big positive. Now, 1 minus that, big negative. Okay, so one more time. This fraction, this thing behind my pen, is a big positive. So 1 minus that is a big negative. Big negative times negative 1/3, big positive. So this goes to infinity. So I diverges to infinity. So I don't have to bother figuring out I1. There's already an infinite amount of area here. So it doesn't matter if this is infinite or finite. When I add them together, it's infinite. This also turns out to be infinite. You can show it. Okay. And I'm just thinking, you know, if this had been a 3, like it is in the problem, right? The only change is that that would still be 3. That would be 3. That would be 3. That would be 3. So the only difference is I would plug in 3 right here. And that would be what? 1 over 27? And you still get the same answer. Yeah. Turn out to be the same. In fact, you know what? And I know it's just about time to break, but if you'll let me do this, let's see. Make sure I didn't make a mistake. It's a 3, right? Okay. Why don't I just change all of these to 3, and then it's exactly the same. So 3. All of this logic's still the same, right? So that's a 3. That's a 3. That's a 3. That's a 3. So let's see. If I plug in 3, that's 1 over 27. 1 over 27. There, how's that? 1 over 27. And the answer's still the same. Okay, so I guess I can remove that star. That actually is problem 31 now. Okay, so if I just change that to 3, 3, 3, 3, 3, 1 over 27, the logic is still the same, so infinite. Okay. All right, so it's break time, 8:07. Okay, we'll break until about 8:20, please. Okay, so break until 8:20. I'll do a little bit more, and then we'll take our quiz. All right, break time. All right, folks, let's continue on. Okay, so I do see a lot that's in the chat. I'll just say some things quickly about it. So yes, for the homework, I realized that when a lot of you were trying to submit it, maybe you couldn't fit it all in one email. Like if you were taking pictures, there's a limit to how much you can send in one email. So you might send it via several emails. If you have something scannable, that's great. I see some of you were chatting back and forth about different ways to do that. That's perfectly fine to figure out some way to scan. A lot of you are mentioning about the weirdness of taking pictures and all that. I know, I get it, and I took that into account. I certainly took that into account when grading your papers and so forth. Okay, so not to worry about that. About time on the exam, again, that's up to you guys. The only thing I promised you, quote unquote, was 50 minutes, but it's up to you if you want to start earlier. I think last time we actually did start earlier than 8:30 or whatever it was. So I think that's going to be okay. So so here's what's happening now. For today, I'm almost done. I only have one more problem to do from 7.8, and then I'll be done with 7.8. And then I'll give you the quiz, and then we're done for today. Okay, so let me go back to sharing the screen. Yeah, I did not look at everything in the chat, but I think most of it was trying to have more time. That's really dependent on you guys. And let's see, if the class decides we want to start, if you're talking about the test at the beginning of class, can we do that? No, that's not an option. It has to be the second half. Okay, that's my rule on that one. Okay, so I'm going to close the chat and share the screen once more. Okay, so at the beginning of class, I said I'll do 7.8, maybe save some for next time. I think I'm going to be able to finish 7.8 today. I was looking at my notes. I think I've done everything I was going to do except for one problem. I'm going to do that one problem, and then I'm done. Okay, and then I'll give you the quiz. So yeah, planning ahead, like for you guys to have more time. Actually, now that I recall, I think the first test, that was when my computer was down anyway, right? So we weren't even meeting per se, but anyway, that's what I think it was. All right, so Tuesday, 8.1, and I'll try to leave you some time for questions, question and answer period, to get them out of the way before the test. So Thursday, 8.1, 8.2, I'll let you ask questions, and then whenever that stops, we break and we start the test, and that's completely up to you guys, up until a limit of what we said, 8:20. Okay, if you want to finish earlier, we can break earlier and we can start the test earlier. Okay, but it will be the second half of class. That's not negotiable. I'm firm about that. Okay, one of the reasons for that is if I have it the first half, then sometimes students don't stick around for the second half and say, "Oh, I'm done with the test. I'm out of here." Right? So you have to stick around and wait for the test in that instance. Okay, so I'll try to give you some time for questions and answers on Tuesday. I'm going to be done with 7.8 in just a few minutes, and then I'll give you the quiz. So we'll be done quite early today. All right? All right, go ahead and keep putting stuff in the chat. So let me do this last problem. I'll check the chat, and then I'll give you the quiz, and then we're done. Okay? Good deal? And so, yeah, it looks like I'm a day ahead again, but I'm not going to stop. I'll keep going in case, quote unquote, something goes wrong. All right, so I'll be done with this, and you know what to turn in for your homework, and you've chatted back with each other how to turn in the homework. Anyway, is fine. Yeah, if you want to give me 5 emails, or one section each, that's fine. Like you want to email me 7.1, and then there's 7.2 and 7.3 and so on, because maybe some of you said it couldn't all fit in one email. I'll take anything. I get it. That's understandable. All right, so 7.8, number 33, and then I'm done. And let me just check that it's the same in your edition as mine. Yes, it is. Integral from 0 to 9 of 1 over cube root of x minus 1 dx. All right, so what's the issue here? The issue is not 0. 0 is okay. I'll be taking the cube root of -1, which is -1. 9 is not the issue. So what's the issue? So where is there trouble? There's trouble at 1. Because if we put 1 minus 1 is 0, cube root of 0 is 0. I'll be taking this 1 over 0, which is not allowed. Okay. So I take the integral from 0 to 1 plus the integral from 1 to 9. Okay. Here's what the graph looks like quickly. So how do you know? Well, you just plug in some easy stuff. You have to plug in 0 anyway, so I plug in 0. 0 minus 1 is -1. Cube root of -1 is -1. 1 divided by -1 is -1. Okay, so 0 comma -1. You plug in 9. Let's see, 9 minus 1 is 8. Cube root of 8 is 2, so 1/2. That's 9 comma 1/2. Okay, now you cannot plug in 1. You can plug in 1.00000001, a little bit to the right of 1. So if I plug in 1.001, subtract 1, I have a real small positive. 1 divided by small positive is big positive, so it goes like that. And if I plug in a number really a little bit smaller than 1, so 0.99999999, okay? If I plug in 0.999999 minus 1, I have a very small negative. Cube root is still a small negative. So 1 divided by small negative is big negative. Okay, so it looks something like that. All right, so I have two pieces. One here, one here. And from what you recall in Calc 1, if this came out to be a real number, positive. If this came out to be a real number, I'm anticipating it's negative, below the x-axis. Okay. Now, if I'm fortunate, one of these would end up being infinity again, then I can stop. I don't have to bother doing the other one. Okay. It turns out in this case that's not true. This is a real number. This is a real number. So I end up combining the two. All right. So I is I1 plus I2. I1 is the integral from 0 to 1 of x minus 1 to the -1/3 dx plus the integral from 1 to 9 of x minus 1 to -1/3 dx. Okay, so I1, I2. Work on I1. Limit as b approaches 1 coming from the left. So you're coming from this side. So b is somewhere like here. And I push it toward 1 coming from the left. Limit as b approaches 1 from the left. Integral from 0 to b. Okay, 1 over cube root of x minus 1 means x minus 1 to the -1/3, right? All right, so limit as b approaches 1 from the left. X minus 1 to the 2/3, okay, power rule, -1/3 plus 1. 2/3 divided by 2/3, there it is, divided by 2/3, means multiplied by 3/2, from 0 to b. Okay, plug in b, b minus 1 to the 2/3. Plug in 0, -1 to the 2/3. Okay, take the 3/2 out. Okay. If I plug in 0.9999999, it's a really, really, really small negative raised to 2/3. It's practically 0. Okay. Now I got to watch out here. -1 to the 2/3. Okay. It means you square it and then take the cube root. Okay. So what's -1 squared? 1. Then take the cube root. What's the cube root of 1? 1. So it's 3/2 times 0 minus 1. 3/2 of 0 minus 1 is -3/2. We get a real number, which means we can't stop. We have to keep going. Okay, so back here, the area right here is 3/2. The integral is negative 3/2, as we know from Calc 1, that if it's below the x-axis, the integral will come out to be a negative. So as I go infinitely far down, I go down, 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 down. You don't get an infinite amount of area. You're bounded by 3/2. The integral is negative 3/2. All right, then I do the same thing for I2. So I1 is negative 3/2. It's not infinity. I can't stop. I do have to keep going. So now I want the integral from 1 to 9 of x minus 1 to the negative 1/3 dx. So I2. Okay, I2, limit as b approaches 1 from the left, integral from b to 9. Okay, so that's sort of like the previous problem. B is on this side. I'm pushing it really, really close coming from the right. So b approaches 1. Well, I'm sorry, this is b approaches 1 from the right. That should be a plus sign there. It actually didn't change the answer, it looks like, but this should be a plus, 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 plus. Okay, limit as b approaches 1 from the right of the integral from b to 9. I think we get the same answer anyway. X minus 1 to the negative 1/3. Okay, the integral is the same. We just did that. So x minus 1 to the 2/3 divided by 2/3 means times 3/2. Limit as b approaches 1 from the right. And I integrate from b to 9. That's a 9 up there. 9. Okay, factor the 3/2 out. So limit as b approaches 1 from the right. Plug in 9. 9 minus 1 is 8. 8 to the 2/3 minus parentheses b minus 1 to the 2/3. Yeah, it turns out not to matter. So b approaches 1 from the right. If you plug in 1.0001, it's a really small positive number. Raise it to 2/3, it's practically 0. Okay, so I was fortunate. If this came out to be b approaches 1 from the left, this would be a very small negative number. It's still going to be about 0. So it turns out to work anyway. Okay, so that's nothing. So 8 to the 2/3 means cube root of 8. Cube root of 8 is 2. 2 squared is 4. Remember, when you have a fractional exponent, this is the power, this is the root. So root is 3. Cube root of 8, 2. 2 squared is 4. 3/2 times 4, answer is 6. Okay, so this area right here is 6. The area here was 3/2. The integral is negative 3/2. All right, so finally, my overall I always means the original integral. I1 plus I2, so negative 3/2 plus 6, and that comes out to be 9 over 2. 6 is like 12 over 2, right? So negative 3 over 2 plus 12 over 2, 9 over 2, final answer. Okay. All right, and I'm finished with what I was going to give you for today for 7.8. I'm done. Okay, so next time I'll get started with 8.1, and I will let you have a lot of time for questions and answers on Tuesday, so that'll save us some time on Thursday for that. So Thursday, if you want to start earlier, that's okay by me. Then ask a lot of questions on Tuesday. In fact, 8.1 does not even look like it's that big a section. We can probably finish it, fairly short amount of time, the way I'm looking at right now. Okay. All right, so I'm done with that. Let me stop sharing, check the chat real quickly. So other things you guys were chatting with. Can we start a bit of 8.1 today? Sorry, I don't think I can do that. I need you guys have to have quite a bit more time for the quiz. So if we start the quiz at 9, you have 25 minutes, but for the quiz, you might need more time, actually. Okay, so let's see. And by the, I realize we're under COVID. This is all different. You got to take pictures and all that. I realize that. I keep that in mind when I'm grading. Okay, so yeah, let's see. We have a quiz today. Yes, we do. Let's see. Okay, it'd be great if we had 1.5 hours for that. That's up to you guys. So if you want to ask me lots of questions on Tuesday, then you don't have to ask as many questions on Thursday for the test. Yeah, I get it. I know some of you were rushing. I realize that. So I try not to be that insensitive, I suppose. Okay, so I think that's it. Any other quick questions? Otherwise, we can start the quiz. All right, so as usual, I'll give you the quiz questions. You get started. Okay, then I'll break you up into your groups of probably either 3 or 4. And then once I break you into your groups, you can leave anytime between now and 9:25. If you say, okay, we're all good, and you just want to leave, I'll let you guys do that. But you probably want to at least look at it and say, okay, try this, try integration by parts, try partial fractions, try this substitution, whatever. At least get that out of the way. Okay, so the real, even though you can do it, the lazy way is to just say, okay, here we are, bye, and just leave. You should talk about it for a while. I mean, that's the whole idea behind putting you guys into groups. Okay, so get your cell phones ready, please. I will get the quiz back up now for a second. And here we go. Oh boy. Okay, I will also read it. Okay, I'll read it for you. I don't know if it helps if I go like this. Now that just makes it more blurry. Well, that looks like the best. Okay, number 1 is the integral of x plus 10 on the top. X plus 10 on the top over x minus 4, x plus 3 dx. I'll say it again. Integral of x plus 10 over x minus 4, x plus 3 dx. Number 2, integral of dx over square root x squared plus 25. One more time, integral of dx over square root of x squared plus 25. So maybe if you can't see this at all, if you just listen to what I say, you'll get it. Okay, so I'll leave this up for maybe another half a minute. Go ahead and get started if you got it. Number 1, integral of x plus 10 over x minus 4, x plus 3 dx. Number 2, integral of dx over radical x squared plus 25. And I believe we're still recording, so if worst comes to worst, you can look at the recording. Okay, so as usual, this is due the next class meeting at the beginning. So what, Tuesday at 7:10 is when it's due. Okay, I'll assume everybody has it. I'll stop to share. If you didn't get it, you can always ask me later. Okay, go ahead and begin, but I'll work on getting you into your breakout rooms. Okay, and then once you're in your breakout rooms, you'll be either with a group of 3 or 4. You can discuss with each other. I will probably be in the main room most of the time, so if you want to catch me, come out of your breakout room and meet me in the main room, unless I'm visiting someone else's breakout room. And then you can leave anytime between now and 9:25, okay? So go ahead and get started. Give me a moment to set up your breakout rooms, and then that'll do it, okay? Okay, you should get an invitation. You should get an invitation to join your breakout room, so please do so right now. See, Michael Vincent, if you can hear me, please join your breakout room. Monk, Erdine, and Michael Vincent, if you can hear me, please join your breakout room.
Through that one. Number 2.
All right, you guys okay?
Yep.
Okay. Any questions about anything, or you good?
No, I think we're good.
You good? Okay. All right. Have a good evening.
See you guys later.